So it's my great pleasure this morning to introduce Carol Watson. She reminded me at dinner last night, I've known her for 20 years, and now I've felt old for the last 12 hours. So, so I was a new assistant professor, got recruited to UCLA, and Carol had just finished a STAR fellowship into the basic mechanisms of atherosclerosis. And it's been really wonderful to see how she has developed an investigative career, but made a transition from the basic research and mechanisms into more clinical research. She has over 120 publications, and interestingly, her very first publication was a co-author with a paper with Judith Folkman in Nature, and that's not a bad way to start if you have to start. She's been funded and held NIH funding for decades. She has played a great role in the MESA trials. She holds multiple leadership positions at UCLA and nationally. She's the director of the fellowship there. She's also the director of the Women's Cardiovascular Center and the Barbara Streisand Women's Heart Health Program. What she's going to talk about today is some of the work that has been going on for some time at UCLA around coronary calcification. And I think this is where her start was, in Linda Deemer's lab. And it'll be a great example of how someone has taken some basic research and translated it into sort of clinical guidelines. So thanks very much, Carol.
Thank you so much for the very kind introduction. And if you guys have, anyone wants to hear any stories about Rob, I'm around, call me. Rob has always been one of my mentors and very favorite people, so I'm grateful for this invitation. So I'm going to talk about coronary calcium, and it's funny because what Rob talked about is exactly true. This is a 20-year story, and I never could have predicted the ending to this when I started. But the one thing I always know, and I think Richard Chang, where's Richard? Yeah, and I always tell my fellows this: your road doesn't have to be straight, but it does have to be steady. And I think this presentation is an example of that. So I want to talk about coronary calcification, where I started with the basic molecular and cellular mechanisms, to then where we, and hi Joel, how are you? And Joel will see a lot of this. A lot of this is from Joel. So a lot of what I was saying is I started as a basic scientist and researching the basic cellular and molecular mechanisms of coronary calcification. And where that was going to end, I thought was going to be in the basic science lab. But then so many things happened and questions arose that you could only answer in different ways. And so follow the questions, because that'll lead you to your next project. I have no disclosures relevant to this presentation. Okay, I'm going to start with how we ever even got there. So it started with an observation by my first mentor at UCLA, Linda Deemer, and it led to a question. And it was an observation of something that everybody else had seen for years. And kind of said, well, it's, nothing. But she said, there's something there. And that's another important thing I want my fellows to always think about. Pay attention, because there's always something out there that you really probably want to think about. Like, why does this happen? Is this something I should study? Then we were led to looking at the molecular and cellular mechanisms of vascular calcification. Then I entered the realm of Joel Kaufman, and I learned about the use of coronary calcium as a research tool, as a marker of atherosclerosis, and how we use it now as a clinical tool. And then I want to think about just a couple of future questions. So starting with the observation. So my mentor, Linda Deemer, who's right there, she had a background in biomedical engineering. So she was always interested in the tensile features of tissues, amongst them atherosclerosis. And being in the cath lab, realizing, okay, there's some plaques that are pretty soft and easy to open, some that are tough and calcified, like what's going on there? So she started looking at chlorinated calcium. What does it mean? And she said, well, this has been seen for years. You can see early publications from Burkhoff talking about the ossification of the arteries, and I'll show you that. And she said, and people said, yeah, it's just what happens when you get old. It's just a passive response to aging. But Linda said, you know what, is it really? Is there something more there? So she noticed there were very many similarities between vascular calcification and true osteogenic tissues, like bone and calcium and cartilage. And so she said, well, maybe this is actually a more active process than people really think. So this is just some paying attention, looking at a bunch of the pathologic specimens. She was able to see tissue that looks all to the world like bone, there on the right and the left, and cartilage and things that look like bone marrow even in atherosclerotic plaques. So she said, you know, maybe there's something more here. When she started to see things that looked like osteoclast-like cells in atherosclerotic plaque, that really made her think, okay, there's something going on here. So you could see these multinucleated cells that look like osteoclasts in resorption pits, just like you have in bone. So she said, let's look deeper at that. And that began us on this journey of trying to unravel the mechanisms of the basic cellular mechanisms. And I was very fortunate to be able to carry out my PhD under the direction of Linda Deemer, along with Christina Bostrom, who was a postdoc in the lab when I was doing my PhD. She's currently the chief of cardiology at the VA in Los Angeles, and Yen Tintet, who's a PhD scientist who was working alongside of me as well. So all of this data is data that the three of us did together. So again, the first thing she said was, let's get an in vitro model of this somewhere. And so we started off by studying vascular smooth muscle cells that were harvested from heart transplant donors who would get just a ring of their aorta so we could culture and their smooth muscle cells. And so that's what we always worked with. And everyone had noticed that if you keep smooth muscle cells in culture for too long, they would become senescent and develop these nodules. So everybody had seen these nodules. Everybody knew that these nodules happen. Most people use it as a sign of these cultures are too old, just throw them away. But Linda said, well, maybe there's something else there. So she said, let me look at these nodules and see what's inside of them. And when she sectioned these nodules, what was the most abundant thing there was calcium. So this is von Cause's staining for calcium, and she was able to see these nodules. She said, they're concentrating calcium. That's interesting. She then looked further, and again, you can still see with histology and von Cause's staining a lot of calcium. She actually x-rayed them, and they looked like calcium. And then she went further. She did electron microprobe analysis looking at the actual content. And it turned out in a ratio exactly similar to hydroxyapatite, the mineral of bone, she was able to see phosphorus and calcium in these nodules in exactly the same ratio. So she said, I think these are more structured than just deposition of inorganic calcium. I think there's some structure here. So when you could very easily see in culture when a cell was about to start forming a nodule and what nodule, where that would be. So if you could see a staining of a baseline culture there over on the left, and then you could start to see these areas condense, and ultimately those areas of condensation would become the nodules. And so looking through all of these, she said, let's look at what's going on from a basic molecular standpoint in undifferentiated cells and when they're condensing and when they're calcified. First, she said, let's see if there are any bone-related proteins that are there. Alkaline phosphatase, it's a non-specific, but a bone-related protein. And you could see that as you go from undifferentiated to condensing to really structured nodule, you would see increase in alkaline phosphatase. content. We then did immunoblots looking at collagen, fibronectin, collagen 1, 4, and fibronectin. So collagen 1 is a protein that is seen in most very highly tensile structures, bone, cartilage, things like that. And you can see if you're in a rapidly condensing, nodule forming culture, they had a lot of collagen 1. They also had a lot of fibronectin, that's panel B, and they had no collagen 4. Collagen 4 is more specific to the vascular smooth muscle cell. In the slowly calcifying cells, there was now no collagen 1, a little bit of fibronectin, and a little bit of collagen 4. So it looks like the phenotype is going from a more vascular smooth muscle phenotype from the non-calcifying cells to a more bone-like phenotype in the rapidly calcifying cells. So when you look at the non-calcifying cells, there's no collagen 1, virtually no fibronectin, and a lot of collagen 4. Again, more of a vascular smooth muscle cell phenotype. And then we started looking at more bone-specific proteins like osteopontin. That's an acidic phosphoprotein that's seen in teeth and bone. It's an inhibitor of appetite crystal formation, and it promotes osteoclastic function. And if you look at smooth muscle cells, there's no osteopontin at all. But if you look at different clones of our calcifying vascular cells, you see a lot of osteopontin. So this is now, again, getting much more specific to a bone-like phenotype. There are also some things that didn't really make a lot of sense to us. So smooth muscle actin, which we expect to see in smooth muscle cells, you could also see that in the calcifying vascular cells. So they didn't lose their smooth muscle phenotype, but they did gain a bone-like phenotype as well. So you could see calponin, which is another bone-specific protein, myosin heavy chain, which is a smooth muscle protein, you could see in the calcifying cells and in vascular smooth muscle cells. So it was an interesting differentiation where you retain some of the smooth muscle phenotype, but also gain a lot of osteoblast-like phenotype. Then we wanted to get to really specific proteins, and that's where Christina Bostrom started looking at bone morphogenetic protein 2. You can tell by the title, it's a bone protein, and then that's something that should not be in vascular smooth muscle cells. So it's one of the TGF-beta superfamily members. It's very well known for cartilage and bone formation expressed in atherosclerotic lesions. People had seen that before. And what no one knew where, how, or why. And what we wanted to see is if this bone-specific protein is seen in these calcifying vascular cells and in atherosclerotic lesion. So actually, Christina was the first person who actually saw BMP, bone morphogenetic protein, in atherosclerosis. And this is the study where we published that. So using in situ hybridization, that's the control panel on your left, and the in situ hybridization in the middle, we could see a lot of bone morphogenetic protein in atherosclerosis. And that has been replicated by many different labs. But that was the first time people said, what is this bone-specific protein doing in atherosclerosis? You can see it co-localizes with the calcium, with von Costa staining. So from all of this, and this is about halfway through my PhD right now, we realized that there was this subpopulation of artery wall cells that have the capacity to become what we thought of as osteoblast-like cells. We were able to see in histologic sections things that look like osteoclasts, active resorption pits, things that make you think of bone. But we didn't know what could be stimulating this. Since it co-localizes with atherosclerosis, we started looking at things that you find in atherosclerosis, like oxidized lipids. So it turns out that we were part of Alan Fogelman's program project grant, which is a very big oxidized lipid studying lab. So we were able to look at all different sources of oxidized phospholipids. And the one that we found had the strongest effect on calcifying vascular cells was oxidized PAPC. And you can see in a dose-response fashion, you could increase the formation of these calcified nodules by exposing the vascular smooth muscle cells to oxidized PAPC. So you can see, and if you use control lipids, that's the green bar, versus 25-hydroxycholesterol and oxidized phospholipids, the blue bars, you see a lot more calcified nodule formation in the presence of oxidized phospholipids. So that then, in our putting together this picture, made the link between atherosclerosis and oxidized lipids and calcified plaque formation. Exposing the cells to oxidized lipids also increased their alkaline phosphatase activity. So it accelerated sort of the bone-like features that we saw in these calcifying vascular cells. And so, for instance, collagen 1, which is very specific for the bone phenotype, more so than the vascular smooth muscle phenotype, in the presence of control media, not much collagen 1, but if you put oxidized phospholipids in there, a lot more collagen 1. If you look at the osteoblast-like cell type, MC3T3E1 cells over there on the right, if you put them in control media, they have a lot of collagen 1, but in the presence of oxidized lipids, they have less. So that was a disconnect we saw between osteoblast-like cells and these calcifying vascular cells. So the first indication that there was a difference in their regulation was that the oxidized lipids stimulated calcification in the vascular cells, but it inhibited calcification in the osteoblasts. And that also made us think about a commonly seen phenomenon, which I'll talk about at the very end. Whereas in the same person at the same time with aging, you get progressive deposition of calcium in the coronary arteries, but decreased calcium in the bones. So this, we thought, well, maybe this is one of the mechanisms. There were so many other things that have since been discovered to be responsible for inducing or inhibiting vascular calcification in these artery wall cells. Many of them are inflammatory signals, things like oxidized LDL, oxidized cholesterol, oxidized PAPC, like I showed you, TNF-alpha, other mediators of oxidative stress, bone morphogenetic 2, as I showed you, can also induce this vascular calcification. And then there are other regulators like MSX2, which are very specific for bone. So it's a BMP2 inducible transcription factor, and it actually controls craniofacial mineralization. So we were able to show that it also controls vascular calcification. Okay, so this artery wall population of cells, and again, we wondered if genes regulating bone formation regulated these cells as well, and we found that that was true. And Linda Deemer is a very theoretical. She really connects dots very well. And she said, you know, the body uses calcification as a mechanism to sort of wall off inflammation. So maybe, she said, maybe an inflammatory stimulus like oxidized lipids is something that the body is mistaking for instance, a invading organism and is trying to wall it off using calcification. And she said maybe that's what this calcification is doing. One of the other things we wondered, so we've seen that these cells could transform into these osteoblast-like cells. We wondered, is it more of a specific transformation from vascular smooth muscle to osteoblast, or is it potentially a sort of mesenchymal stem cell that could maybe transform into a bunch of different tissues? So we started to look at that. So the one thing we know is that bone marrow-derived mesenchymal stem cells are positive for CD29 and 44 and negative for CD45 and 14. So we wanted to see if our calcifying vascular cells had the same pattern of surface markers. And it turns out that they do. So if you look at the flow cytometry up in the top left corner, the M1 cells are control cells, control marrow mesenchymal cells, and M2 are our calcifying vascular cells. You can see positive both for CD29 and positive for CD44. In the bottom panel, we had a different cell type that was positive for CD14, and you can see the spike there, but not in our calcifying vascular cells. The same thing for CD45. So the same pattern of surface expression was seen in mesenchymal stem cells and in our calcifying vascular cells, which raised the question, is this just an example of a vascular smooth muscle-derived mesenchymal stem cell that is available to be transformed into a number of different cell types based on the conditions? So this is when I was young and still, we actually made USA Today because this was, you know, a pretty new, and again, it's the doctor's answer to curiosity. That was Linda Deemer's curiosity, like, what is this and why aren't people studying it? So it's a really good example of what Linda always says, one man's trash is another man's treasure. So pay attention, keep your eyes open, you'll never know what you'll see. But as I said, it wasn't news to anybody in the 1800s that there was, quote unquote, ossification of the arteries in the artery wall. So this is from Virchow in sometime late 1800s. And he actually showed that using these very rudimentary tools, such as microscopes, that he could see ossification in the artery walls. So it's past his prologue. A lot of our new discoveries are things that people have actually seen a long time ago. Okay, so how can CAC then be used? So we know that a truism, you're not supposed to have calcium in your arteries. You're just not supposed to. And when you do, it often identifies atherosclerotic plaque. There's very, very, very good data now that the more calcium you have in your arteries, the more the atherosclerotic plaques. And so we can use that then as a subclinical marker of atherosclerosis, and that's where MESA comes in, and that's where my colleague Joel Kaufman comes in. So the multi-ethnic study of atherosclerosis. So I'm probably telling you guys things you've already heard, because I'm sure you heard it from Joel. MESA is a really landmark study, because if you think about the Framingham Heart Study, which is an amazing study, taught us so much about risk factors and cardiovascular disease. It's a very important study in a little town in Massachusetts, which is less ethnically and racially diverse and probably not emblematic of what the US is today. So MESA is meant to be that way. So 6 US field centers recruited 6,800 healthy men and women between the ages of 45 and 84 when we first recruited them, about 50 men and women. Ultimately, it was meant to be about a quarter of each of these ethnicities, but we ended up with 34% white participants, 28% African American, 22 Hispanic, and 12% Chinese. And these are the field centers. Washington is the coordinating center for the study. So the main subclinical measures of atherosclerosis that when MESA was initiated said we want to see if we can use subclinical atherosclerosis measures to determine clinical events, etc. And the main two we were looking at were coronary calcium and carotid interval medial thickness. And both of them were considered to be potential, like, new subclinical measures that we could use clinically. Early on, we realized that if you're looking at future cardiovascular events, coronary calcium is a better predictor than CIMT. So this is one of the first studies that we published, which showed that looking at the coronary calcium score and the hazard ratio per 1 standard deviation increment in terms of clinical events, it was about 1.9. And if you looked at multivariable analysis of coronary calcium, the event rates per 1 standard deviation increase in CAC was about 2.3. And that compared much more favorably to carotid IMT, which had an event prediction of about 1.3-fold for each standard deviation increase. So it turned out that CAC was a better predictor, and that's where we focused most of our time on. And I'm going to talk now about some of the work that you've probably heard, and if you have, let me know, and I can skip right through it on air pollution from Joel, because this is one of the, I think, one of the best examples of how this can be used. And this is all Joel Kaufman. And I can't tell you how lucky you are to have this guy here, because literally he's visionary. Because I remember when we were first involved in the air pollution study, Joel, we thought, what a great idea, but like it's kind of optimistic. We'll see what we can get, because it's a really in-depth study. And the when you guys see actually what Joel was able to do, you'll be equally as impressed. So being in Los Angeles, we have a real strong interest in air pollution. So in case you haven't heard, the state is on fire right now. And so all that particulate matter, I cannot look at it the same way, Joel. I showed them some pictures last night of the fires that the picture was taken from our roof on our hospital. We're burning all around. And all I can think of is PM 2.5, PM 2.5. So PM 2.5 is not good. It's those really tiny, tiny microparticles that you suck deep down into your lungs, and they create a lot of havoc. It's funny, like I can't go to a barbecue anymore. There's a lot of things now that you don't think about, that you are kind of slowly poisoning yourself. So there's a lot of PM2. Sorry, my husband says I suck the fun out of so many things for him. Okay, so there's a lot of PM 2.5. You know, where we live in Los Angeles, we live by our cars, and if you happen to be near a roadway, you're getting a lot of PM 2.5. Turns out that the ports are even worse. So when those big tug ships come in, they're getting a lot of PM 2.5. It's all around you. And that is, again, those are these particles that you can suck really deeply down into your lungs and create this inflammatory milieu, which is not good for anybody. Now, a lot of the work on PM 2.5 initially was on the pulmonary effects, which makes sense, but there's a lot of cardiovascular effects as well. So again, you know, you have a lot of filtration mechanisms that make sure you don't suck those big particles down into your lungs, but the smaller particles really don't get effective. So they can, these inflammatory stimulus that get set up by all of this PM 2.5 that we're inhaling all the time is just not good. So this study is literally Joel's, I don't know, it's like your, I don't know, I think of it as your seminal paper. Am I wrong? It's a big part of it. So this is a study that was published in the Lancet. Yay, Joel. And the whole idea behind it was that long-term exposure to this PM 2.5 is not good. So, and it can be associated with cardiovascular risk. And previous studies had actually shown that this was probably true, but they had shorter follow-up, and they really were limited by a number of variables, which we thought, as Joel thought, could be overcome by the MESA study as a perfect example of how to do it. And he did some really smart things, and I thought the MESA Air study was just a beautifully designed study. So to test a priori if air pollution could affect progression of coronary artery calcium and carotid integral media thickness, and looking at a number of pollutants, including PM 2.5, nitrogen oxides, nitrogen dioxide, and black carbon. And the MESA study was, the MESA cohort was really an important cohort to be able to do this in. So the coronary calcium, as I mentioned, CAC was part of the study planned into it. And so participants had repeat coronary calcium, which allows you to do that. We were able to do so many interesting things because of these, longitudinal follow-up. Common carotid CIMT was studied at least twice as well. And so I learned so much about air monitoring by this whole study. So we partnered with our colleagues at USC for air monitoring, and we're monitoring about 100 homes per city, and they were monitored in different seasons because you have to account for, you know, weather, fires, etc., barbecues, things like that. Outdoor monitoring and indoor monitoring. we're able to get these really granular geospatial maps of where PM 2.5 was located and concentrated. Really beautiful. But so again, it makes you a little paranoid about going outside. But the other thing that I thought was so smart that you did was we enrolled participants at UCLA and also in New York from different areas, but sociodemographically very similar, but different air quality. So we enrolled participants from Riverside County, which is a inland empire area where all the ocean breezes blow in all of the air pollution, and then the mountains trap it there. So it's got terrible air quality. And then Venice, which is a less affluent part of West LA, so very sociodemographically similar to them, but they're right near the ocean, lots of ocean breezes, air quality is much better. So can compare the event rates between these two areas. So this is the maps of PM 2.5 and nitrogen oxide, and looking at Baltimore up on the top left, Winston, North Carolina on the top right, St. Paul, Minnesota on the middle left, New York City on the middle right, Los Angeles on the bottom left, and Chicago on the bottom right. So the black dots are bad. And you see a lot of black dots in Los Angeles, they're the bottom left. On the right is nitrogen oxide. You see, again, a lot of black dots on the right, but you also see a lot of black dots in New York. So I don't know, who has worse air quality, Joel? New York or Los Angeles? Oh, stop it. I think that they're really close, right? A close second? Okay. And you can see this graphically. Again, Los Angeles, yeah, California over there, more PM 2.5. But okay, New York is worse than some other areas. Okay, we're not all bad. And this was the central illustration from that article, which basically showed that you can correlate the long-term average PM 2.5 concentration with coronary calcium. And that was something that, like, literally, I can't explain enough how amazing it was to be able to show that. So, yay, Joel. So, CAC increased consistently in the population. As we get older, CAC does increase, but it increased more rapidly the more PM 2.5 you're exposed to. And we did not see the same correlation with carotid interval medial thickness. Again, showing that CAC is really your best measure of subclinical atherosclerosis. One of the other things I thought was so nice about what you were able to show, Joel, is that, you know, we're doing better. So, like, this is a beautiful graph showing the trajectory of annual PM 2.5. Each one of those lines is a participant. And you can see it's all going down a little bit. So I think your work with the EPA and with regulations, we are getting a little bit better. I remember when I was in elementary school and high school, Joel, we used to have smog days. You know how you guys have, well, some people have snow days. We would have smog days. My kids have not had one smog day, not one. So I think we're getting better. Okay, I'm going to go to another study that we did looking at CAC to try to understand about HDL. So as you know, epidemiologically, HDL is associated inversely with coronary heart disease. The older studies, Framingham, many older studies show that the higher your HDL levels, the lower your atherosclerotic event rates. But many studies shown a little bit different as well. Some have shown that not all HDL is protective. There's some low HDL states where there's not increased risk of atherosclerosis. There's some high HDL states where there's actually increased atherosclerosis. So the picture is a little more murky than that sounds. So we wondered if part of that murkiness in that picture had to do with the different demographics of the population. We thought obesity probably had a lot to do with it. And as sort of a marker of metabolic dysfunction and obesity, we looked at metabolic syndrome. So our hypothesis was that HDL is not as protective against atherosclerosis in individuals with a metabolic syndrome. So we characterized our MESA cohort according to the presence or absence of metabolic syndrome, and then we further stratified them by HDL level. So we stratified them by low HDL, HDL less than 40, intermediate HDL between 40 and 59, or high HDL above 60. And what we were able to see was that if you were in the entire cohort, you had more coronary calcium if your HDL was less than 40, and you had higher clinical event rates. These were event rates. If you had metabolic syndrome, you had higher event rates overall and more coronary calcium, but there was a U-shaped relationship between HDL. Really low was bad, but really high was bad too. And actually, the lowest clinical event rates were in those who had that moderate middle range HDL. If you didn't have the metabolic syndrome, you had sort of the classic pattern of what we think of HDL should do. Higher event rates if your HDL is low, and lower event rates if your HDL is high. So it looked like having the metabolic syndrome was a differentiator. Again, in the entire cohort, the event rates were highest if your HDL was low. In the metabolic syndrome cohort, the event rates were lowest if your HDL was in that mid-range, and if you had no metabolic syndrome. It was that classic pattern of the higher the HDL, the lower the event rate. And we could see it right there. So these are the survival curves, event-free survival. If you had low HDL, blue, they had the worst outcomes in the entire cohort, as you see there on the left. If you had in the entire cohort either HDL 40 to 59 or above 60, the event rates were better and not different. If you had no metabolic syndrome, again, you had that standard same pattern as the entire cohort. But if you did have the metabolic syndrome, actually the best survival was in that mid HDL range, the green line. And if you had either too low or too high HDL, either the red or the blue lines, you had significantly worse survival. So we wanted to see if there was an interaction between HDL and the different parameters of the metabolic syndrome, the dyslipidemia, the insulin resistance, the obesity, and the high blood pressure. And we were able to actually see the only parameter of the metabolic syndrome that made a difference was the obesity. So, and that was the measure of obesity we used was waist circumference, and there was a statistically significant interaction between the HDL effect and the waist circumference. So it looked like this. If you look at the hazard ratio for CHD on the y-axis and the waist circumference going across on the x-axis, if you had that mid-range HDL, the green line at the bottom, you were the referent. If you had low HDL, regardless of what your waist circumference was, you had higher event rates. But what about the people in that high HDL group? Those are the people we used to think of as the healthy, protected people. Well, it turns out that there was a relationship between the waist circumference and the event rate. So if you had high HDL and you had a normal waist circumference, your event rate was actually lowest of all. But as the obesity went up, the waist circumference went up, the event rate went up. So it looked like there was an interaction. So as my mentor, Alan Fogelman, who's a big HDL researcher, always says, HDL is a chameleon molecule. It's a big ball of fat, and it will adopt the properties of whatever environment you put it into. If I put HDL into a healthy, exercising, non-diabetic environment, like Framingham Heart Study did, it's going to look pretty good. It's going to protect it. But if I put it into an obese, pro-inflammatory, pro-insulin resistant population, it's probably not going to look as good. So again, if you have a whole bunch of inflammation around and you put HDL in there, you're going to get a whole bunch of pro-inflammatory HDL, which may not only not protect you, but it may actually harm you. Okay, but how can we use CAC as a clinical tool? Well, it turns out that it's a really good clinical tool as well, and that makes sense. CAC identifies plaque. So if I have higher CAC, I probably have higher plaque. And we know from MESA that it's a really good surrogate marker of atherosclerosis. Of interest, when we looked at the different genders and race ethnicities, you can see the green bars, CAC is highest in whites. It's actually lowest in African Americans, and it's intermediate in Chinese and Hispanic, both for men and women. But regardless of what race ethnicity you are, CAC predicts events. So if you're Black, again, Blacks have lower CAC than any other race ethnicity. But if your CAC is equal to 0 and you're Black, you have a lower event rate than if your CAC is higher than 300, a direct stepwise increase. Same thing with Chinese. The event rates are lower overall, but CAC 0 has a lower event rate than any other CAC strata. Same with Hispanics and whites. So even though different race ethnicities have different CAC levels, it's still a great predictor in everyone. So even if you look by age, CAC is less prevalent in younger people. It goes up as we age, but even by young age, if your CAC is 0 versus greater than 300, your event rate goes up. So even though the baselines are different, it's still a very good predictor. And it predicts clinical events very well. So this is looking at the overall MESA cohort. If your CAC is 0, that's the red line. If it's 1 to 100, that's the line just above. And if it's above 300, that's the top line. Their rates are higher with higher CAC. And that was looking just at hard cardiovascular events, death, myocardial infarction. If you're looking at any CHD event, unstable angina, or vascularization, the event rates are higher. Again, the higher the CAC is. And that's true for every race ethnicity, as I showed you. It's true for every age strata, as I showed you before. It's true for both men and women. So CAC is a really, really, really good predictor. And we now know that CAC above 300 is associated with a hazard ratio for future CHD of almost 10-fold. It's very significant. So that makes it a really good clinical marker of the atherosclerosis, and we can use that. Now, one of the problems with CAC is that I think the clinical application in the very beginning got ahead of the research. So the question became, who should get a CAC? So we know it's a feature of atherosclerosis. CAC's coronary calcium scoring is very important and can give you a lot of data, but who should get that scan? Because if you look at, like any paper, you'll get these advertisements. Check out your coronary calcium scan. You can get it now for $100. You should do it. So it really was an example of technology preceding the data, but I think now we have such good data, it's very clear, I think, who should get a CAC score. One of the things we want to do is make sure that if we're doing it, it's adding value. So we have a number of risk scoring schema that put in risk factors and things like that and try to predict who has a certain risk, and they're pretty good. If we're going to use another technology like CAC, we have to prove that there's added value to that above and beyond the risk scores. And that has been shown in MESA. So looking at CAC in terms of different risk scoring, so Framingham, the blue lines, Framingham plus CAC, Framingham plus carotid intermediate thickness, Framingham plus brachial mediate flow, Framingham plus 3D reactive protein, et cetera, et cetera, et cetera. The one that makes the biggest difference is adding CAC to Framingham, and you can see that with the receiver operating curves there. And that's true for incident coronary heart disease and total incident cardiovascular disease. So CAC adds value above and beyond what Framingham can give you, and that's not true for other subclinical markers. So how do we use it? Well, how about if so the one thing I think is clear, CAC should be used as a decision aid for intensifying preventive therapies. It's not meant to go chasing the CAC number, trying to modify a CAC number, going to the cath lab if you have a certain CAC score. It's meant as a decision aid to help you decide who gets more intensive therapy. So let's look at using CAC to inform the number needed to treat for blood pressure treatment intensity. So If your blood pressure is less than 60 and your ASCVD risk less than 15, a CAC of 0 has a pretty low event rate. So those are people that maybe you can, not aim for a systolic blood pressure of less than 120, maybe 130 or 140 might be fine. If you have CAC above 100, that identifies a really high risk group, and maybe they do need the much more aggressive therapy. CAC can also perhaps inform aspirin decisions. There's been so many trials. We used to give it to everybody. It was in the water. But then we said, no, okay, give it to nobody. And probably neither of those are right. But is there a way we can be smarter about who gets aspirin? Well, if your CAC is equals to 0, you're actually probably not going to benefit a lot from preventive aspirin. So the numbers needed to treat, shown as the y-axis there, if your CAC equals 0 and your CHD event rate is less than 10%, you have to treat 2,000 patients with an aspirin, or you're going to see one event avoided, and that means you're going to get a lot of bleeds. If you have a CHD rate above 10, the number needed to treat is lower, but it's still a lot. And what we learned with the recent 3 aspirin trials is that many times you'll cause as many bleeds as ischemic events as you'll prevent. If your CAC is really high, though, the number needed to treat get really, really low, and the number needed to harm for bleeds, as you see that red line going across, the number needed to treat is well below that. So it makes sense then. There are a number of primary prevention patients who have really high CAC scores who probably really should get an aspirin. So we've kind of thrown out the baby with the bathwater with the recent aspirin trials, but there's probably a way we can be smarter about targeting who gets aspirin. What about a statin decision? Yeah, CAC, that's one of the best things you can probably do with CAC. And this is from data, this is a illustration that's from a publication that I and many members of MESA, like Bill Greenland, Michael Blaha, etc., wrote in JACC on CAC. And we basically wrote a paper very similar to my talk, where we talked about the molecular mechanisms, the research applications, the clinical applications. And this is what we, even before the guidelines came out, this is what we put out there. We said, CAC can be used to help inform your decision about statin. So if you have an ASCVD estimated risk less than 5, statin's not recommended for anyone. But between 5 and 7, that's when the guidelines say to start thinking about it maybe. And that's when CAC can probably help you reclassify. So if it's a 5 to 7.5 or 7.5 to 20, CAC is actually probably a really good way to sort of further refine who gets their statin. One of the things that a lot of people, and Michael Blaha has really pioneered, is the thought about the power of 0. If you have a CAC equals to 0, then that may be a patient that you really can de-risk and de-intensify preventive therapies. And basically, when he looked at, this is from Michael Blaha, shown there in the corner, one of our MESA investigators, he said CAC equal to 0, which is the bottom line down there, it's like a negative risk factor for development of future disease, because it really does identify a lower risk group. So you can maybe downgrade the risk. But remember, not all plaque is calcified. We know sometimes you'll get a non-calcified plaque, and that's important too. So the risk is not 0 if your CAC is equal to 0. It's lower. But looking by an angiogram, we sometimes see calcified plaques, mixed plaques, and non-calcified plaques. And you can have a non-calcified plaque that ruptures and causes an event, just as a calcified plaque. And there are some studies that actually show that the risk is greater for those non-calcified plaques. So this is a study looking at cardiovascular risk by CAC score and stratified by plaque type. So if you have a calcified plaque, that's the red line at the top. If you have a mixed plaque, that's the yellow line in the middle, and a non-calcified plaque, that's the blue line on the bottom. And in this study, the outcomes were worse in the non-calcified plaques. It's one study, but it is some data. But as I showed you earlier, CAC equals 0 does not mean 0 event rate. So in our MESA cohort, if you were Black and you had a CAC equal to 0, your 10-year event rate was 3.9%. It's not nothing. So there is risk. It's lower for certain ethnicities, but look at even for Hispanic patients, CAC equals 0, 3.1% risk. If you look by age, it's even greater. If your CAC equals 0 and you're 75 years of age, there's still a 5.6% in your risk. If you are a male, the risk, and female, the risk is about the same, but CAC equals 0 does not mean 0 risk. So what are some future directions? Okay, as I mentioned earlier, there is this calcium paradox that we call it. Why is the body depositing calcium in the arteries where it's not needed instead of depositing in the bones where it is needed? So, and I told you one of the things we saw is that the different mediators that accelerate plaque vascular calcification inhibit bone calcification. So maybe that would be one area of future research, to try to figure out, are there strategies we can use to inhibit plaque calcification and improve bone calcification? And again, that's what I showed you here. In oxidized lipids, you go towards a more calcified vascular cell phenotype with collagen 1 deposition. You go away from that osteoblastic phenotype. Another area that we think is very interesting. So I met with Dr. Abba yesterday, and I was like a fangirl, because I was like, I have followed her work for a long time. Dr. Deamer and she was one of the first people looking at aortic calcification at a time where we were looking at vascular calcification. So both of us were sort of like kind of the rogue people in the wind, and we were really very interested in your work, and you've been seminal in that over the years. So we really are still really interested in the relationship of coronary calcium to aortic valve calcium. We think there's something there, and we'd love to further collaborate with you, Dr. Abba, to look at that. So I just would like to conclude by saying this subpopulation of artery wall cells has the capacity to become osteoblast-like cells. It can be induced to an osteogenic type phenotype by inflammatory stimuli, oxidized lipids, atherogenic stimuli. CAC is a really, really powerful research tool as a subclinical marker of atherosclerosis. It's a really powerful clinical tool as well, but it needs to be used properly. It really is a great decision aid. It helps you decide when to intensify preventive therapies. We don't know if we can modify, or if it even makes sense to modify vascular calcification, because Linda Deamer, again, who's got a biomedical engineering background, she looks at the tensile strength of various plaques. And if you look at a completely circumferentially calcified plaque, that's pretty stable. But what's really unstable is the interface between really hard calcium and really soft plaque. And that can be a nice for plaque rupture. But it's not known if modifying that is possible or even useful. And again, I just want to acknowledge all of my MESA colleagues. These are the UCLA co-investigators, but there are a million MESA investigator staff participants that have put into a lot of heart and soul into this data. I acknowledge the huge, enormous contribution of Joel Kaufman, who is one of my mentors and friends, and like about the most humble guy you've ever met. And just these huge collaborative studies require a lot of funding, and some of the agencies that have funded. Thank you so much for your attention. I'd be happy to take my questions. Yes. Yeah. So, yeah, that study needs to be done, and it hasn't truly. But there's a number of sort of suggestive pieces of data. A lot of it from MESA, and like in our paper in JACC, we go through the data that is available. It's not our gold standard randomized controlled trial data, but there is pretty good data that you can more appropriately tailor therapies and lead to decreased event rates with appropriate use of CAC. Yes.
So I was correct, the recommendation on counseling if it's available to users, but don't send people for it.
So no, so it's basically so what we said in the 2013 guidelines of cluster, which I was a member of, is basically you match the intensity of therapy to the intensity of risk. If you're a high risk patient, they get high intensity scan. Moderate risk patient gets moderate intensity scan. Then low risk patient, we say they don't need anything. Don't recommend a CAC in them. Don't recommend a statin in them. You're low risk. You don't need anything. So it's not recommended for low risk. The current recommendations for CAC is it can be useful in that intermediate risk patient between 5% risk and 20% risk. It's a big range, I know. But if they're really high risk by risk factors, I'm not going to talk you out of treating them just because their CAC is 0. You're going to treat them. If they're really low risk, they don't need anything. It's just that intermediate. Fall into that category. A lot, but I'm really persuasive.
So, in the venous system, when we implant pacemakers, and we have to extract it, oftentimes we see quite a bit of calcium around the leads, binding the leads to the epithelium of the circulating vein, superior vena cava, even inside the heart, and it's not unusual doing a generator change to find a generator that's encased in calcium.
So cool.
To the point that looks like
I was trying to wall off that amazing organism.
so calcium.
It's useless, yeah. So yeah, that's the problem. Is again, calcium can be a lot of places. So I've seen patients that have been given a calcium score of like 2,000, and then the next one that they, for whatever reason, they get another one and it's 0. So someone mistook their mitral annular calcification for coronary calcium. So that's the problem. A lot of calcium looks alike in our rudimentary imaging. Yes.
Lovely talk. You should
I'm not sure. Tell me when to stop. Here?
Yeah. What I found fascinating, we know that men, but when you stratify like
It's kind of a great unifier, right? Well, so, hold on, Joel, what do you think?
right, so is it calcium?
Right. So even though these look like they are similar, the men are 15 years younger than the women when they have comparable CAC scores. But I am still surprised at how many of our participants still have CAC equals to 0. And I don't know if that's because we just live healthier lives. I don't know.
Thank you very much.
Thank you.